What's up, calculus students? Mr. Messer coming at you with a new and improved, hopefully, 7.2 homework. Changing up Unit 7 from past years, hopefully to make it easier to understand. 5 lessons instead of 4 in the past, and what we introduced in Lesson 2. It's a key thing is the concept of like displacement. How far did we travel and in what direction? If you remember from physics class, if you take your like velocity and you multiply it by the time in which you're uh, undergoing that velocity, you get a displacement. If you take your meters per second over the course of the seconds at which you traveled, you'll get meters. Okay, the seconds will cancel. All right. Well, what happens if your velocity is changing? What we talked about in the lesson is like, okay, that's easy to calculate if your velocity, say, is consistent. If you're traveling at 20 meters per second over the course of 3 seconds, you went 60 meters. But what would happen if your velocity is not consistent? Well, conceptually, we could say take all of the velocities, multiply them by all the split seconds in which we're traveling at those velocities, and you'd get that displacement. What that looks like visually is like an accumulation or an area under your velocity. Like with the 20 meters per second over 3 seconds, we could say like, what does 60 look like? 60 looks like this area, 20 times 3. Well, this accumulation looks like an area. If you accumulate your velocity, you get a displacement. Now I'm going to actually start on the graph ones because I think it's easiest to understand the sign analysis that we've been doing and how we are adding a new layer to things, okay? So I'm going to start with this one. We had, in the past, looked at the signs of our derivatives. Now, velocity is just a rate of change of position. It's the word physics teachers used, so they didn't have to say, how's the rate of change of your position? So they're saying like, well, like how's your position changing? We'll call it velocity. We've looked at signs of derivatives. And now, again, this is when we were like, okay, the derivative is positive until 3, negative until 6, positive from 6 to 7. And we're going to write these values small. Now, what's important again, and I tried to bring this up on your first homework lesson, is that these are times. This is not like the guy moving. He's not going to move to a position of 3. He's not going to move to a position of 6. This is like what's going on over the course of the time. This is a time axis. We'll go back and we'll look at what the dude would look like, okay? And the sign of a derivative tells us if something, the original thing, is increasing or decreasing. We talked about how position increasing means I'm moving to the right. Position decreasing means I'm moving to the left. Position increasing, I'm moving to the right. But here's the next layer, okay? If we accumulate our velocities, now here is the symbol for accumulation. You know this symbol to be an antiderivative, but it also means accumulation. You'll find out why like we're using the same symbol for 2 different things next class. For right now, you're going to say, well, I'm going to accumulate my velocity. And you can see it was giving you in the problem that the accumulation of velocity, what's up? They're a huge stack. I'm gonna get my class through it and then give her the extras.
Okay, sounds good. Thank you.
If I accumulate my velocity over 0 to 3, they're telling you that that's 5. If I accumulate my velocity from 3 to 6, I have this negative 3. And if I accumulate my velocity from 6 to 7, they're just like showing us in the graph that that's 1. Now, what does this mean? Well, this is how much my position increased. This is how much my position decreased. This is how much my position increased. What we get is that the accumulation of your derivative, the accumulation of your rate of change over an interval tells you how much your original function increases and decreases. So it's this extra layer. We didn't really worry about values, but now we can. For example, if x of 0 is 2, well, I then go and increase my position. I go to the right 5. I now have x of 3 equals 7. If I have x of 3 equals 7, and from 3 to 6, I decrease my position by 3, I now have x of 6 is equal to 4. If I then increase my position by 1, x of 7 must be 5. Now, some of these questions are easily answered if you just understand this, like, okay, accumulation of velocity tells us how far we traveled. So what is my position at time 3? If we want to be proper, this is just kind of like scratch work. If you want to have like full credit on a free response question, which you will have on your test, it's all free response questions, you need to show that you took your initial position, you added your accumulation of your velocity, the accumulation of your derivative, the accumulation of your derivative from 0 to 2, and you got 2 plus 5, which is 7. Cool? Now, if I asked you, what is the displacement total? Well, displacement is like the change in your position. You will see there are two ways that you can calculate this based on what we've already done here. You could say it's like, well, what was the accumulation of all my velocities from 0 to 6? What was the accumulation of all of my derivatives to find the change in the total? Well, it was this 5 minus this 3 plus this 1, which is 3. Okay, 5 minus 3 is 2 plus 1 is 3. Or you could find that, oh, I knew my position at time 6. It's my ending position. I knew my position at time 0. That's my starting position. How far away did we end versus where we started? I started at 2. I ended at 5. 5 minus 2 gives us 3. And this is the key for next lesson, is understanding, like, how can we find these accumulations if they're not given to us? Well, we can use our positions to subtract them. Final position of the particle, if you wanted to show this correctly, here's what you would have to do. You'd say my position at time 7, multiple ways to do it, is either equal to my position at 0 plus all of my accumulations of my derivative of my velocity from 0 to 7. Or you could say I started at 0, I added 0 to 2, I added 2 to 4. You could go with all of them. Let's say you already showed what your position at time 3 was. You could say, well, I'm going to start with my position at time 3 and then add 3 to 7, or add 3 to 6 and then add 6 to 7. There's all these different ways of finding your final position, which we got was 5. Now, the dude. What is happening with the dude? Now let's go to this axis, but again, this is like the dude moving, where this is position, not time. Time kind of floats above. We started at a position of 2. Here's my dude at a position of 2. For 3 seconds, my dude's position increases until he gets to a position of 7. He increased by 5. So he goes to the right. He ends up at a position of, whoa, look at that neck. He ends up at a position of 7. This was when time was 0. This is when time is 3. Again, this is not a time axis now. This is a position axis. We're kind of like connecting our time axis, where we found our positions based on the signs of derivatives and our accumulations, to this. And a lot of you are probably skipping this because you're like, I get it. It's just very important. He then moved to the left to get to a position of 4. That position of 4 was when time was 6. He then moved to the right to end up at a position of 5. He moved to the right and he ended up at a position of 5 when time was 7. That's what we just see. The sign of our derivative tells us if position's increasing or decreasing. The accumulations of our derivative is our velocities times times, derivatives times intervals, totals. How much did we move to the right? How much did we move to the left? Okay? I'm going to do this one again because it's easier. And then I'm going to go back to page 1 where like you have the graph of the derivative. So let's do it all. Heads up. We know a position at time 3. This is going to be important for going backwards. What happens? Okay. We start at 0. We got 1. My velocity is negative. That's my derivative of position, my rate of change of position. It's negative until 1. It's positive until 3. And then it is negative until 4. I'm going to move 1 over a little bit just so I have some space to write down the positions. Okay. Negative until 1, positive until 3, negative from 3 to 4. All right. That is telling me my position is decreasing, increasing, decreasing. The sign of a derivative tells us if in our original guy is increasing or decreasing by this many y's per x. Here it's meters per second, feet per second, whatever, okay? That's what we remembered, like the interpretation of a derivative. At this moment, this thing is increasing if it's positive, decreasing if it's negative by this many y's per x. Now it's feet per second. Cool. Now, the additional step is the accumulations of my derivative. My velocities times, which looks like the area under my derivative. From 0 to 1, I get negative 2. From 1 to 3, I get 6. From 3 to 4. Now, I'm writing all these integrals down because it's going to be important to show all of this work on the free response portion. It is not something necessary for this homework, but for full credit on free response questions, unfortunately, you need to kind of have this all written down and you need to show all of your calculations done versus what is going to be easily kind of understood and done. Now, what happens if I go backwards? I have x of 3 equals 2. Well, let's go to x of 4. This is telling me how much I'm decreasing. This is telling me how much I'm increasing with my position. This is telling me how much I'm decreasing with my position. If I decrease 3, my final position's at negative 1. Now let's think about this, and here comes the calculation I'm going to do. My position at time 1 equals my position at time 3, but I need to kind of go backwards to figure out where I'm coming from. I will subtract my displacement from 1 to 3. This is very similar to having your position at time 3 equals your position at time 1 plus your displacement and then solving for x of 1. It's the same deal where it's like if I increase by 6 to get to 2, I must be coming from negative 4 or 2 minus 6 equals negative 4. If I decrease by 2 to get to 4, I must be coming from 6. Or what is the calculation shown from that? X of 0 equals, you could have x of 1 listed, x of 1 minus integral from 0 to 1 of x prime. And that's going to be 6. You could say x of 0 equals x of 3 minus the accumulation from 0 to 3 of the derivative. That would be 2 minus 6 plus 2. 2 minus 6 plus 2, boom. Yo, that's a negative 4. Shoot. That means I just realized I was like going off the wrong thing. I must be coming from negative 2. 2 minus 6 plus 2, negative 2. Whoops. And I also just like hid my face. I feel like there's a way. Let me pause. We're back. Figured out the shortcut. All right. Sorry about that. 6 is definitely not right. Negative 2 minus 2 gives you negative 4, plus 6 gives you 2, minus 3 gives you negative 1. Now that's actually the position from 0 to 4. At 0 and at 4. My bad. Gosh, I'm off. Hopefully you're understanding this. I'm not paying attention to what the question is asking. X of 4 equals x of 3 plus the accumulation of my derivative, the accumulation of my velocities. That's going to be -1. And then I talked about that earlier. X of 0 equals x of 3 minus all of my accumulations from 0 to 3, because I'm going like back in time, and that gave me -2. -2 minus 2, -4 plus 6, 2 minus 3, -1. Everything makes sense. What is the displacement from 0 to 4? Well, overall, watch how you could find this two different ways, and this is the key to the lesson. Overall, I could either do -2 plus 6 minus 3 when I'm talking about the accumulations. That's 3 minus 2 is 1. Or I realized that I could have had my ending position and I subtract my initial position, -1 minus -2, to see I ended up to the left 1 of where I started. That's what we say about displacement. Okay, we talked about distance. We will talk about distance more. Why don't you go ahead and skip this question? You could find this actually. Well, we can kind of introduce distance. Distance is total amount traveled. We're going to talk about it more next class. But like, let's think about total amount traveled being like, oh, if I go to left 2, I traveled 2. Introduction to this. If I go right 6, right 2, I've traveled a distance of 8. If my distance is 13, I'm going to have to go 5 to the left. That's 8 minus 5, which is 3. So my answer here has got to be -5. Hopefully we understand that. We weren't asked about anything in terms of positions. We're good. Okay, now let's go back to, I have my calculator, okay? I have a calculator and I have situations where I'm given a velocity. Noticeably, right off the bat, I kind of know I can't take the antiderivative of this velocity. Like, I can't find a position function. But I do have a velocity, I do have a derivative, and I do have my calculator. What's the key here? My calculator can accumulate. My calculator can do a very quick numerical process to find the area under my derivative. What are we going to be doing for all of these? What we just did for the velocity graphs. Only you will find the accumulations or the areas. You will always, if you have a calculator, start by graphing your derivative. Okay, my derivative is my velocity. It's x prime. I'm graphing my derivative. I will make sure I adjust my window. If I'd like to, I can zoom fit this. Usually things are going to look nice in this unit, but it won't always. And boom. Now I'm wondering if I could snip this and put it in here. I can't. So whatever. What does this show? And I am going to zoom fit this just so I can see. Remember, zoom 0, zoom fit. Okay. What this shows is my velocity is negative until some point. It's positive until the end. That's my derivative. Great. Now, let's say we were to do a sign analysis. Okay, well, let's break out our long number line. What's the key points about our derivatives? When they change signs, that's the zeros of my derivatives. It's not the min of my derivative. The min of my derivative is when my derivative changes direction. That's going to be when x double prime changes sign. That's going to be my acceleration changing sign. Velocity decreases means a is negative, v prime is negative. Velocity increases means v prime is positive. We can go into that more when we're asked, but we're good right now. Cool. We need to find this intersection. Now remember, there's two ways you can do second calc 0, but what we talked about in class is, since we're going to be doing this often, always have y equals 0 graphed. You don't see it, but it's there, and you can second calc intersect, enter, enter, enter. We got that this intersection, which I'm going to call A, and I'm going to write down, is 2.71238.9. And we talked about how, since we're doing this a lot, make sure we're comfortable storing values. X store as A, or you have the value just pulled up. You could just press store and you're just going to say answer store as A. Cool. And now we are going to have your calculator calculate the accumulations. They're not given to you. You're going to find these areas by doing either in this, which is good the first couple times we do it. Second, calc this integral from the bottom to the value you want, and you will be visually able to see the accumulation of your derivative. Now, what does this mean? What are we going to write down? Well, x prime is negative. That means x is decreasing the area under my derivative. And I'm using x prime because this is going to be applicable for f and for any other situation. The accumulation of a derivative is how much we are increasing or decreasing. So the accumulation from 0 to a of x prime is negative 2.077. Now, this is fun to see, but I'm going to show you it's easier to use on the home screen because we need to keep those values down, and we want to use the entire value. Let's accumulate from a to 5. And the accumulation from a to 5 of my derivative is 4.218 ... Boom. Now we kind of know positions. We know where we started. They fortunately gave us a position. And we know how my position's changing. We know how much my position decreases, how much my position increases. Let me show you the calculations in the home screen. They're easier to do, or just as easy to do. We will use Math 9. 0 to a, and instead of retyping the equation, we have alpha F4, which brings up vars Y1, and this automatically plugs in what you have in Y1. And you'll get this negative 2.077, which we found. You can go and reselect and go from A to 5, and we're going to get that 4.218, which we saw. If you want to write it in here so it makes sense, great. If you want to write it in here so it makes sense, great. Now, I'm asked, find the positions when the particle changes directions, find the positions at the start and the end of each interval. Boom. Here's where the particle is going to change directions. Here's the start. Here's the end. What are the calculations you need to show for a free response question? Well, obviously, you don't have to show that x of 0 equals 3. It's given to you. But you do need to show x of a, which is listed off, is your initial position at 0 plus your accumulation, your displacement of your derivative. Now you have to do this calculation. I started with 3. My position decreased 2.077, and I got 0.922, ... Okay? If I have my position at 5, multiple things you could do here. I'm going to show both ways. You could say, well, I started at 0. I could look at my accumulation overall. Now watch what I'm going to do here. If I put 0 to 5, it's going to be this negative 2.077 plus this 4.218, which will give me this 2.141. Great, that's my overall displacement. I end up right 2.141 units compared to where I started. But you could also say, I already know my position at A. I know my position increases from A to 5, 4.218. As long as you have this work kind of shown where you know where this value is calculated and you're using the previous one and you're kind of showing everything that makes sense to us, you'll be fine. But unfortunately, they're a little strict about like work shown. So I have my position at time A, which I should have written down here, 0.922. My position increases 4.218. My position at time 5 needs to be 5.1 something. Boom. Got it? That's the unit, okay? And accumulation of a derivative, how much your position increases or decreases, or how much your original increases or decreases. I gotta go teach pre-calculus, and then I'll be back to finish this up. All right, we're back. Cool? Show your work. Maybe for the rest of your homework, don't show your work. Be prepared on your test. And on your quizzes, if I ask you, show your work. Whether that means you don't use this and you're just going to show your work down here, it's great. If you do use this, make sure you understand it's not sufficient unless you like show the exact calculations that you do. All right. The rest is kind of repetitive. Graphing your derivative. Zoom fitting. I'm not going to show the graph here. You will hope that there's one intersection, because if there's two, it's just a lot more work. We'll call this A. We'll list off A. This is something that I will always do, and I recommend you always do. We're going to 6. We know x of 0 is -4. Again, this is the time, and I'm writing down the position. You know the derivative of your position, the rate of change is positive and then negative. We know my position's increasing, then decreasing. The accumulation of my derivative will tell me how much I'm increasing and how much I'm decreasing. I'm not going to show all the work up here. I'm going to show the work down here. I'm going to store x. It changes once you find that intersection. Store it as A. I will math 9 it. You could do this in the graphing screen if you want, but I find it's easier here because you could just use alpha F4 to get to vars y vars. And it's also easy to change this from A to 6, and you have everything done, and it's, everything you need. Oh, that's crazy. I'm going to go to the right 6.433, but then I'm going to go to the left 6.474. So I end up barely to the left of where I started. Watch what happens. This will be fun for me or to anybody else. If I go 0 to 6, I'm going to get a barely negative number. That means my displacement over the time interval is just a little bit to the left. It's like I pretty much end up where I started. We got x of 0 is -4, x of a equals x of 0 plus the integral from 0 to a of x prime. So that's -4 plus the integral from 0 to a. And I get a position of 2.433. And then x of 6 equals, what do you want to do? Do you want to go from 0 and then just like do your overall displacement from 0 to 6? Sure. Do you want to go to A and then just do your displacement from A to 6? Sure. Regardless, I mean, I already have that x of 0 is -4. I just calculated my overall displacement. Here's one way to get the answer. Okay, there's one way to get my finishing position. Let's show you a different way. Make sure the values make sense, like -4 plus 6, 2.4 minus 6. Okay, back to -4. All of this should make sense. The other way is to go from x of a, which is that 2.433, then add your displacement from a to 6. The accumulation, your velocities times your meters per second times your second, will be able to go backwards and understand it's like y's per x's per x to figure out how much my y's are increasing. Areas under derivatives, changes in total. Okay, boom. All right, heads up, heads up, heads up. What if I give you a position in the future? We kind of saw that with the graph question, so we're ready for that here. Should not worry you, provided everything makes sense. Everything that we've been doing makes sense. Adjust your window 0 to 5, zoom fit if you choose. I'm not going to draw the graph. I'm going to hope for one sign change, and if I have more than one, I will be upset, but I will figure it out. All right, looks like we're close to 2. I'm going to find the intersection. I got one sign. Oh, I got 2 sign changes. Poop! I got an A, and I got a B. We got to make sure we store that as B. There it is. Got to find the other one. Easy word of advice. You want to find the other one? Press up to go to y equals 0. Just go along y equals 0. Enter, enter, enter. Store that as A. Write down what A and B are somewhere. This is so important for your quiz and your test. 0.145. I mean, I can have this up while I'm writing, so I should use it. We want to use that entire decimal. In math, we like to just be as accurate as possible, which means use all the decimals provided until we get the final answer. We saw that my velocity was negative. My derivative is negative, then positive, then negative. We know that your position is going to decrease, increase, decrease, which means I'm moving left, right, left. Again, I could have, after doing this, after doing this, we could understand motion on a motion axis. It's important to understand it, especially for the later problems. Motion. Position now is the x-axis versus time. This is a time axis, this is a time axis, and then I'm writing down positions. Position started at a position of 3. I moved to the left 2.077 until I get to a position of 0.922. This is at, 2.712 seconds. And then I end up going to the right a bunch till I end up at a position of 5.141. This is how my dude moves. This is going to be very important for the future when we're trying to find max and min positions. Cool. All right, let's do some work. The accumulation of my derivative, how much I moved, in what direction. Now, you can do it in this graph, or just, let's go math 9, 0 to A of y1, alpha F4 y1. Okay, I can see, I can just like look. I'm moving to the left a little bit. The area under there is a little bit. And boom, that is confirmed here. I go to the left a little bit. I go to the right more. I then go to the left, I think a decent amount, right? From what I remember from looking at the graph. Yeah, a lot. You can see the area here looks to be more than the area here. So my velocities accumulated must produce bigger displacement. Add them all together, you can figure out how far away you ended from where you started. We're going to end to the left of where we started. That's important to know. It's like I moved to the left a little, to the right a bunch, but to the left more. I'm going to end further to the left than where I start. Now, what am I given? X of 5 equals 4. Let's think about this. What if I were to go backwards to find x at this 1.989? Well, I have to take this value, subtract negative 13 to get the position of 4. How can I go opposite? I want to add that 13. Or, since we're going backwards, instead of adding my positive and negative displacements, we'll do the opposite. We'll subtract. Two ways. You can either say, oh, my unknown future position equals my known position plus my displacement. And then you can solve for x of b by adding the 13.547 or subtracting the negative. Or probably what I would do if I were you is to just like understand I'm going backwards. I'm doing the opposite. I have my position, but I need to subtract this negative displacement. You'll find how in the future you could switch the way these numbers appear and it will take you backwards. It will tell you that you'll go, plus 13.574 to figure out where you came from. If you want to try that out, do it. Like if you change this from B to 5 to 5 to B, you'll see it's the opposite. Anyways, 4 minus this number is adding a positive. I must be coming from a position of 17.574 here. To then go to the left and finish to the left of where I started. I still need to work my way back to where I came from. I know what x of b is. Again, I need to subtract this 9. I'm going to increase 9 to get to 17. I need to subtract the 9 to figure out where I came from. So it's going to be around 16. Make sure the things are in the right order. I'm writing x prime just so we know this, because like sometimes when you use the word v, you realize that v is just a derivative. And when we switch gears to future units, we're going to go back to x's and y's. So we're going to use f prime. Anyways, I talk too much doing these videos. Already had that. That minus that. All right, this makes sense. I am close to 8.565, so that I add 9 and I get to there. And then where do I come from? Well, I'm going to come from somewhere to the left of 4. I know that. My overall displacement, which could be used if I wanted to. I want to go from 0 to 5 and accumulate all of it. This will tell me overall, I end up 4 to the left of where I started. I'm going to have to come from like an 8.909 value. Now let's make sure like we could get it either all at once or one step along the way. X of 0 will equal x of a minus the integral from 0 to a. So if I want to, I can find my x of a, subtract the integral from 0 to a, which I found earlier, but it's easy enough to just repeat it. And there you go, 8.909. And if you wanted to double check, I have my ending position of 4, subtract my overall displacement, and I get that 8.90. Okay? This all should make sense to you guys. Starting position, displacement. Next position, change directions. I stop. Displacement. I've stopped. Displacement, boom, I end. Big money, no whammies, no whammies. One sign change, one sign change, one side change. Zoom, fit, stop. Come on, stop. Beautiful. Beautiful. Now, I don't actually know, like, do I move to the right more than do I move to the left? Not sure, not sure. Maybe like really quickly, I'm just going to find the accumulation from 0 to 3. Be like, yo, what is my overall displacement? This is how far I go left, right? That's how far I go. Overall, I go right a little bit more than I go left. That's cool. Okay, make sure that makes sense. But let's like split it up. And again, I could have looked at the previous one in terms of motion. Like, let's break out our motion axis where it's the position, not time. And it's the position of 8.909, moves to the left 8.565, moves to the right to 17.545, and then moves to the left even more to 4. Cool? That's motion, and my dude. All right, X towards an A. Cool. Velocity is positive and negative, my derivative. My A value. My position increases, then decreases. These are times. My area under my derivative from 0 to A. If you already have it, Y1's now changed. So this is going to be all different. Like, it's so easy to do in your calculator. It's the one thing where it's like actually easier in your calculator than on Desmos. A to 3. I end at a position of 2 at time 3. I've gone to the left to get there. I must be coming from 5.116. Let's make sure we understand it. My position at time A equals my position at time 3 minus A to 3. If you want to do it the other way, where it's like X of 3 equals X of A plus, I feel like most students understood it last year the other way. So 2 minus that. I must come from a position of 5.116 so that I go and my position decreases that to end there. Where did I start from? Well, you could do your overall displacement, or you could go off of A. I go to the right 4.164 to end at 5. I must be coming from like somewhere around 1. 0 to a under my derivative. Already found. I want to subtract that from x of a. Coming from around 1.952. Okay, so motion. New axis, position axis. Times hovering above. My dude is moving to the right, to the left. What does he do? He starts at 0.952. Here he is. Takes him 2.06 seconds to go to 5.116. Here is where he's at after 2 blah, blah, blah seconds, 8 seconds. He then goes back to 2. Here's where he ends. This is after, screw on the neck, 3 seconds. Okay, this time axis helps us understand this position and motion axis. If I want to find displacement quickly, I don't have to split it up, is important. If you ask your calculator to just accumulate without looking at everything, and if I wanted to split this up, I could. And if I wanted to graph this in y equals, I could. Close to being the same thing. But understanding that if you accumulate everything, your calculator is going to add all the positive displacements, subtract all the negative displacements. It's going to count for everything. This number being negative says overall, my position at time 8 is 2 to the left of my position at time 1. I ended 2.040 left of where I started. Now, how do you get there? Well, obviously we saw we could move right and left a couple times, but overall, I end up to the left of where I started. Oops. If you wanted to graph, you could. Overall, I end up 16 to the right of where I started. X of 9, my position time 9, is 16.311 more than X of 1, or I ended 16.311 to the right of where I started. I kind of showed you earlier. You want to find something quickly without doing a full sign analysis? Understanding your calculator's doing everything. It'll incorporate how much I go to the right, how much I go to the left. It'll incorporate my displacement, how much my position changes. Like, here's what it would look like. Watch. I know x of 2 is 3. Let me see if this makes sense to you. X of 2 is 3. I don't know what happens. I'm just going to assume I don't know what happens. But I know the overall displacement from 2 to 4, that's very important, is the following. Minus 8.148. I don't know like what all goes into that, how much I go right to the left. I could look into that if I wanted to, but I'm not going to. If I wanted to find my finishing position quickly, I have my starting. I know my overall displacement. I have my ending. This is where we write down the work. X of 4 equals X of 2 plus my displacement, my accumulation of my derivative. Accumulation of my derivative tells us my overall change. X of 4 equals 3 minus that value, 3 plus that negative value, not minus that value. And I get negative 5.148. If I, yeah, I'm not even going to show the work here. I'm just going to do it all at once. And voila, we get our answer. I don't like getting the answer really quickly. It doesn't put context into things, but it should make sense. Overall, I ended up to the right of where I started. If I looked at just this, I don't know what happens in between, but I know overall, over the 3 seconds, I've displaced 1.047 seconds. Feet, not seconds. That's how much I ended up to the right of where I started. Boom. If I wanted to go in the past, 2 different ways to do it, just like I showed you. You can either say x of 6 equals x of 0. You want to get in here, you got to come this way. There, you're in. You made it in the video. And then solve. 3 equals x of 0 plus whatever this number is. You're going to have to subtract this number, whether it's subtracting a positive or subtracting a negative. Or I'm trying to figure out the past. I know the future. Subtract the displacement or go back in time, 6 to 0. Don't do that. You could, 6 to 0. We'll talk more about that next unit. If you go back in time to get that. 6. Now I don't want to do it. I'm gonna show you just this part. Yo, in hindsight, y1, y2, y3, y4 would have worked out great because it seems like all of these equations are repeating. Next. Okay, overall, over these 6 minutes, I end up 3.14 to the right of where I started. If I end up 3.14 to the right of where I started, where did I come from? Well, I ended up at 3. 3 minus that will tell us where you started. I'm not going to do the calculations. You shouldn't have to do the calculations. You should understand. X of 1 equals X of 4 minus your displacement from 1 to 4. Maybe I'll show you the other way to do it. I don't want to, but watch. If I go 1 to 4 of t sine t, this is a little bit different from pounds. What does this mean? I end up 1.556 to the right of where I started. Watch what happens if I flip these numbers. This is like, oh, you travel to the left to go back in time to where you started. Like, it's giving you the value that you're adding. You could do this. Honestly, I don't want you to do it, but you could do this. Or you could solve for x of 1 here. X prime is equal to v, you know that. So -2 plus this or -2 minus that, it's all going to be the same things. I want to make sure this makes sense. I displaced 1.55, so I have to go to the right to get to -2. I must be coming from a further negative position, -3.556. I'm just going to write the equations down, not do the calculations. Minus to go back in time. Recommendations, guys. It's not memorized. It's understood. You probably find the displacement first. You understand what that means in context of moving forward in time from 0 seconds to 3 seconds. You understand, okay, I'm ending at a position of 5. How did I get there? Understanding you're doing the opposite. These are good questions to get you prepared for the free response portion of your test, which is the entire test. Never mind. Your test, your next test, the Unit 7 calculus test is all free response. Are the particles moving towards or away from each other at time t equals 0? All right. Let's have some fun here. This is my cosine graph. That's my sine graph. Okay, I'm familiar with this. All right. I know particle B is located at position 3. Let's talk about a position graph. Here's position 3. Here's B at time 0. Particle B is the y2. At 0, the velocity is -5. If I plugged in 0 into VB, velocity is -5. That means my position is decreasing. I'm moving to the left. Cool. Now, to figure out if I'm going towards or away from A, I need to figure out the position of particle A. All right, well, the position of particle A at 0 will equal the position at 5. And then again, you're going to subtract your displacement from 0 to 5. Make sure you go back in time. A is y1. So keeping that in mind, I'm going to math 9, 0 to 5, y1. I could do this in the graph, but it gets a little bit weirdy. Sorry, it's alpha F4. So I have a position of 3, subtracting. Okay, so I go to the right 2.141 to get to the position of 3 at time 5. So that means I must come from 0.858. Okay, particle A starts at 0.858. This is the position. This is at time 0. Particle A's velocity at 0 is 0. Okay, so not moving at all at 0. Since B has a negative velocity and it's to the right of it, we're moving towards each other. I probably should write x prime, which equals v of a of 0 equals 0. This is a little excessive. I'll say this right now. Yeah, you could skip the free response questions. If you skip them, it's okay. This is a heavy homework. We've done enough of it. It's starting to get repetitive. So I'm finishing with these last 2 questions. We'll do plenty of free response on the 5th lesson day. All right, I got to find the times and positions. I need x b of 1, which equals x b of 0 plus the integral from 0 to 1 of x prime. I need v b of 1. Oof. Okay. 0 plus that's 0. My position of B at time 0 is 3. I'm going from 0 to 1 of y2 because it's B. Point 7.833. Cool. My velocity at 1. I go up to y2, I press in 1, and it's positive 7.38. Okay, cool. So, particle B is at 7.833, and it's moving to the right. Particle A at 1. I already know A at 0, so why don't I find 0 to 1 of that. At 0.858 plus the 0 to 1 of A's equation. .353. What is the velocity? I will change, I'll press trace. Here's y1. I want v of a1. Here's y1 at 1. Press 1, trace 1. It's negative 0.989. That means A's position is decreasing. It's moving to the left, away, based on positions and velocities. All right, I think I can answer all this. X of A of 0. My position at time 0 was 0.858. My velocity at time 0 was 0. So towards or away from the origin, neither. No. Oh, jeez. That was B. No, A 0. Okay, yeah, we're good. B's velocity was negative 5, and its position is 0. A's velocity is 0, and its position is 0.858. Neither. Horrible question. I probably needed to give you velocity. B's position at 5 I didn't find. Okay, I'm getting all screwed up. No. A at 0. Here's A at 0. Here's A at 0. B at 5. I gotta find X and B. At 5. Three plus y2. Okay. I am left of the origin. That's my position. Again, understanding this is looking at my position of my dude at time 5. My velocity of my dude, particle B at time 5, is -5. Which means I am left of the origin, moving left. We are moving away. All right. Good questions, making sure we understand positions and velocities for these, very much free response questions. We already did the graph problems because they're easier to do. These we'll do more of. In preparation for our test, so I'm actually okay if we just like skip them from now because we've really covered everything. Just if you want to look over things, part A and B, we already did. Part C is going to be easy. Done. Part B is going to be easy. This is from last year. It's a good question we'll do probably during class. I'm not going to do it. All right, later. No calculator next class.